Hello, my name is Dave Pridmore, and I'm presenting Understanding Power Efficiencies in Electrical Heating, How to Save on Energy Cost. Before we get into the technology, I want to first comment on the current state of industrial electricity. Electricity is getting more expensive. The Bloomberg article shown here describes how 600 workers at the second largest aluminum mill in America lost their jobs because the plant can't afford the electricity bill. Summer 2022 is projected to set the highest electrical rates on record. These runaway energy costs hope to be curbed by a recently passed Inflation Reduction Bill, which, in part, aims to incentivize clean energy technology. So the evidence is clear. Heat treaters can no longer overlook electrical inefficiencies in their systems. The more important point, however, is that all heat treaters have access to these incentives and rebates if they clean up their energy use. So today, I'm here to find some of the low-hanging fruits and uncover some of the electrical blind spots in electrical heating systems. To start, here's a summary of the variables at play in an industrial electric heating system. There is typically a dedicated service line for the heating circuit. This is where power is billed. Electrical billing is made up of some combination of kW, kVA, peak demand, and power factor. kW demand, or kilowatt hours, is typically billed directly, and kVA demand can be billed directly or indirectly through power factor penalties or peak demand charges. Also noted on the circuit here is an ammeter and voltmeter. This shows how kW demand is only a part of the total picture of power consumption. kVA demand is a more useful way of understanding power because this is what you measure as amperage through the circuit. This correlates to peak demand charges in a power bill and circuit breaker sizing in electrical systems. The first part of an electrical heating system is the power controller. Historically, ignitron tubes, used prominently in the 30s and 40s, were really just rectifiers to control power to an application. Another type of power supply is the VRT, or Variable Reactance Transformer, which is actually a control and transformer in one. The core in a VRT can be electrically desaturated or saturated to control power. Finally, there are the more sophisticated control systems like the common-day SCR and IGBT control types. Each of these control types has an ideal place for use, and it is important to consider the control type because it can have an impact on the upstream power quality and quantity. Next in the system is conversion to high current, low voltage with a transformer. Transformers are typically divided into air-cooled or water-cooled. The high current then needs to be delivered to the load. This can be accomplished through water-cooled cables or large copper cross-sections. After the transformer, everything is essentially a heating element. If you look under the green cables here, it shows Joule's law, which states that heat is proportional to current squared. One of the value propositions we'll cover later is reducing this high current circuit outside the furnace to improve efficiency. The load is then energized. Commonly used loads are graphite, molybdenum, or silicon carbide. An important variable at play in the load is also the type of current, AC or DC, and the physical size of the circuit. Finally, probably the most important variable here is time, which means how are you operating your furnace? Do you use it at 100% full tilt every time, or do you scale back to 50% power for long, slow runs? All of these variables can significantly impact the power quality of your furnace. In summary, these are the electrical components and variables at play in a typical heating circuit. The next step is to examine the relative efficiencies of these components in practical scenarios. Here's the first example of an electrically underperforming furnace. This case demonstrates why operation of a VRT at low power is electrically inefficient. The furnace is powered with a VRT rated at 375 kVA. This equates to 125 kVA per zone at 46 volts and 2,717 amps. A typical run was performed, and the power quality was assessed in only the heating circuit. The cycle shown here consists of a ramp up to and hold at 1800 degrees Fahrenheit. The run was completed without any issues. On the surface, everything looks fine. That is until we examine the electrical characteristics of the furnace. The graph below shows a total power consumption of the furnace for this cycle. The red area represents kVA, and the blue area represents kW. The reference here on the right is the beer mug analogy of the power triangle. The blue area, kW, is real power, or the power that's doing work in the furnace. The red area, kVA, incorporates the wasted power, or the foam on top of the beer, which no one wants. This electrical trend is what we expect to see. As the furnace is ramping up in temperature, it takes more energy at higher rates as the furnace is heating up. Then, when the furnace reaches the soak phase, the energy requirement drops down to a plateau because we're simply maintaining a heat. Also note the line above, which is the maximum rated electrical capacity of the furnace at 375 kVA. This is remarkable because the real power required for this run never exceeded 120 kW. In other words, the maximum power of this cycle was only 26% of the ideal rated electrical capacity of the furnace. This is not good for power quality. The best way to understand this is to compare the total kilowatt hours with the total kVA hours, shown in the table below. Impressively, only 43% of the power in this run is actually doing work. That's about 60% foam on top of the beer. The essential trend here is that with a VRT, the more a furnace is used under its rated electrical capacity, in this case at 26%, the more inefficient it is electrically, and these inefficiencies impact the bottom line. Going back to the standard model, more kVA demand is billed either directly through kVA billing or indirectly through power factor penalties or peak demand charges, which is shown on the table on the left. How much? An impressive way to describe this is with the peak current demand. With the VRT, there was a peak demand of 250 amps. However, with the kVA inefficiency addressed, the peak demand is reduced to 125 amps, or 50% less. This introduces the comparison between a VRT and an IGBT MFDC power supply. An IGBT MFDC power supply is 91% efficient compared to the VRT's 43% efficiency. This means that the IGBT MFDC power supply is passing real power more efficiently. It is also important to note that the IGBT MFDC power supply was sized for the full capacity of the furnace, which means it is also running at 26% full capacity. Going back to the beer mug analogy, a VRT is like a fixed size mug. The less you fill it, the more foam you get. With an IGBT MFDC power supply, the mug grows and shrinks with the cycle, always giving you mostly beer and little foam. The graph here shows the same run, but now with an IGBT MFDC power supply in red. The total power, kVA, being very close to the real power, kW, of the furnace. In summary, for case 1, VRTs running at low set points put a disproportionate burden on the power grid. An IGBT MFDC power supply is an adaptable alternative that optimally shrinks its footprint for each use case. Before moving on to case 2, this is a good opportunity to clear up the difference between kW and kVA savings. Up until now, we've really just discussed the kVA portion of the story. kVA is commonly described with the power triangle shown on the left. On the x-axis, there's kW, which is the real power or the power that's doing work. And on the y-axis, there's kVAR, which is the imaginary reactive or wasted power. These are 90 degrees out of phase and are vectorially added to calculate the kVA. The action shown in the triangle demonstrates the changes we discussed in case 1. A reduction in kVAR with the same kW results in lower kVA. So what about kW savings? Remember that kW is the power that is doing the actual work in the furnace, and accordingly will always be the largest component of power. This is the working power, and the objective is not to reduce kW to 0, but to reduce any unnecessary losses outside of the hot zone. This is accomplished through reductions in resistance and reactance, which is shown on the impedance triangle on the right. Similarly to the power triangle, the impedance triangle has real and reactive components, which are 90 degrees out of phase. The difference here is that the vectorial sum is now impedance, measured in ohms. Impedance reduction in a furnace circuit lowers kW demand. This is demonstrated in the simple circuit shown in the lower right. There is a resistor with impedance Z that has current passing through it, I. The equation shows that power is directly proportional to impedance. This is why it's important to reduce impedance outside of the hot zone. So, how do we eliminate excessive resistance and reactance? Going back to the comparison with a VRT power supply, an IGBT MFDC system reduces impedance through not masking, but total elimination of reactance with direct current. And it lowers total resistance by shrinking the transformer and moving it closer to the heating elements with what we call close coupling. Here's another way to look at the impedance triangle and how it impacts power within a system. An ideal circuit is shown on the right. This circuit shows a standard impedance model of a transformer and load. This is essentially our standard model of a furnace heating circuit. The components of power include resistance and reactance in the primary circuit, resistance and reactance in the secondary circuit, and resistance and reactance in the load. The important note here is that the only component doing work is resistance in the load. The other components have no useful value, and every effort should be taken to reduce them. The concept of reducing resistance in a circuit is pretty straightforward. Reduce the physical size of the circuit. But what about reducing reactance? In the previous slide, I stated that reactance is eliminated with direct current. What does that mean? The equation for reactance is shown below. Reactance is a result of alternating current and is a function of both the area of the circuit as well as the frequency of the waveform. From the equation here, you can see that as area and frequency increase, the reactance also increases. However, with an IGBT MFDC system, direct current has no frequency, and the exaggerated secondary losses are eliminated. It is also important to note that reactance is derived from the magnitude of changing current. Therefore, the high current secondary of a transformer has an exaggerated impact on the reactance losses within a system. This is another reason why we focus efforts on minimizing the size of a high current circuit within a system. This leads into the second example of an electrically underperforming furnace. Case 2 looks at the power impact of water-cooled cables. This is a 5-zone furnace rated at 615 kVA. The furnace has 3 side zones at 150 kVA, 1 top zone at 55 kVA, and 1 bottom zone at 110 kVA. A typical run was performed, shown here, and the power quality was assessed in only the heating circuit. The cycle consisted of a ramp up to and hold at 2200 degrees Fahrenheit. The run was satisfactorily completed without any issues. The water-cooled cables in this case consisted of 4 14-foot cables, 4 18-foot cables, and 2 20-foot cables. In the picture here, you can see the cables draped over the catwalk between the VRT power supply and the furnace chamber. The power loss in the cables was then measured across multiple furnace set points. The power loss was calculated by measuring the amperage and voltage drop across the cable. Power loss is then calculated by taking the product of that voltage drop and the amperage. The graph here shows the cable power losses by percent power. The purple line, for example, shows that at 80% power, this cable is continually dumping 5.5 kW into the water, whereas at 40% power, this cable is only continually losing 4 kW. Remember that everything after the transformer is essentially a heating element. Water-cooled cables are just a resistor wrapped in water. This introduces the value proposition of reducing this high current circuit outside the furnace to improve electrical efficiency. If we go back to the standard model and replace the water-cooled cable with a closely coupled IGBT MFDC power supply, a clear electrical benefit can be seen. The pictorial schematic above shows the closely coupled transformer shrinks the secondary circuit and reduces the unnecessary losses outside of the hot zone. This close coupling makes the impedance triangle smaller and results in lower kW demand, lower kVA demand, better power factor, and lower peak current demand. Specifically for this run, the total kVA hours was reduced from 1180 to 928, a 21% reduction, and the total kW hours was reduced from 939 to 901, a 4% reduction. So, how does an IGBT MFDC power supply work? Here's an IGBT MFDC pictorial schematic. Starting on the left side, the input into the system is 3 phases, 60 Hz AC. This shows 480 volts, but other main voltages can be used. Within the control, the power is first rectified to a 650 volt single-phase DC bus. It is then smoothed with a capacitor and inverted with IGBTs into mid-frequency. The output of the control is 650 volts at 1000 Hz. This is then distributed to the MFDC transformer and stepped down to low voltage, high current power. Within the MFDC transformer, there are diodes that then rectify the 1000 Hz AC waveform into high amperage direct current output. This DC current is then delivered to the load. A key part of this system's value proposition is this high voltage transmission. When the three phases are rectified up front, we start with a higher voltage. That higher voltage allows us to step down the secondary voltage at a higher ratio. This correlates to lower current draw and lower peak current demand. At the bottom of the screen is an MFDC transformer that is used in an IGBT MFDC system. The picture shows how the transformer and rectifier are combined into one unit. A summary of the advantages of an IGBT MFDC system include balanced three phases, lower primary current draw, reduced reactive losses with DC, and smaller transformers because of higher frequency power transmission. Some of the limitations of the system include three-phase power is required, water cooling is required, and higher component losses can make this less efficient in some scenarios. In conclusion, and as a summary for this presentation, we have evaluated the typical electrical characteristics in a vacuum furnace. We have discussed the limitations of the predominant power supply technology, and we have presented solutions offered by IGBT MFDC control types. Thank you very much for joining me today. For more information, you can find us at www.romanmfg.com. Thank you.